In this video, we'll look at chromatography theory. In the last video, we selected HPLC or liquid chromatography as our method of choice for separating carbohydrates in products from our hypothetical company. Here I show a selection of possible carbohydrates that you might find in plant-based products. We chose HPLC because carbohydrates are molecules that have a polarity that cannot be easily separated by gas chromatography. Whenever you report the results of a chromatographic experiment, you must report at least 4 critical parameters. Here, I identify the stationary phase of the separation. Here, I identify the mobile phase of the separation. Here, I identify the flow rate of the mobile phase. And here, I identify the detection method. At a minimum, these 4 parameters must always be reported. The result of injecting a mixture of 6 carbohydrates into an HPLC is a chromatogram shown here. In the chromatogram, I can see peaks corresponding to each component of my mixture separated. The area under each peak is proportional to the amount of that solute. Separation in chromatography is based upon differential partitioning and migration of each solute between the stationary and mobile phases. You should remember from organic chemistry that any chemical will selectively partition between 2 different phases. In this case, a green chemical is selectively partitioning in this aqueous layer, and less of it is found in the organic layer. We can define a partition constant, such as Kd, as an equilibrium constant expressing the relative concentration of our solute A in either the organic or the aqueous layer. In this case, Kd is less than 1 because our solute preferentially dissolves in the aqueous layer. The same phenomena are at play in chromatography, but in chromatography, solutes are partitioning between their affinity for the stationary phase versus the mobile phase. In liquid chromatography, the stationary phase remains fixed in the column and is usually some porous spherical material, and the mobile phase carries the sample through the column, achieving multiple opportunities for each solute to equilibrate. If we're doing a single extraction, the difference in partitioning a collection of solutes might not be that significant. However, small differences in partitioning affinity become amplified as a sample moves through a column. Here we see a sample injected, and as it moves through the column, it separates, and one compound comes off, then another, another, and another. The result is a chromatogram in which each of our components, in this case, a collection of carbohydrates, 1, 2, 3, 4, 5, and 6, are separated. As I mentioned before, the area or height of each peak is proportional to the quantity of each of these solutes or analytes, and each of these analytes can be identified by its retention time, which is given by the time that elapses from the injection to the maximal height of the peak. An additional important feature of a chromatogram is shown here as T0, sometimes called T minimum, and this is the elution time of an unretained peak. In the case of liquid chromatography, this distortion in the baseline is where we see the solvent that the sample was dissolved in eluting from the column. Now let's take a look at chromatogram parameters in more depth. The chromatogram I'm showing here is for gas chromatography. So in this case, the unretained peak corresponds to methane gas. As I mentioned on the last slide, the retention time of a solute is defined by the difference between the injection time and the maximum for the given peak. But there is an additional parameter known as the adjusted retention time, or T prime, and this is the difference between the retention time and T minimum, as shown here. This parameter is particularly important for calculations in chromatographic theory, as you'll soon see. Also, when we are comparing two retention times, there is a factor known as alpha, or the relative retention time, and that is simply the adjusted retention time, T prime, for two different peaks, one divided by the other. In this case, this were T prime 1 for the octane peak, and T prime 2 corresponds to this unknown peak, then the alpha for the unknown peak relative to the octane peak would be given by this ratio. We're interested in alpha because it is a measure of how well resolved two peaks are, as we'll soon see. In addition to the four parameters I just defined, there are a few other parameters that occur often in chromatography theory. One is the retention factor, and that is the adjusted retention time divided by the minimum retention time. Also, instead of speaking in retention times, we often speak in retention volumes. And the retention volume is simply the retention time times the flow rate of the mobile phase. And just as we have a minimum retention time for a solute, we can have a minimum retention volume for a solute as well. For various reasons, it is sometimes useful to express the x-axis of a chromatogram in volumes rather than time. Finally, I want to again emphasize that beyond the location of the peak in time, the area under a peak is proportional to the amount of the solute, and when examining parameters related to the quality of separation, we often will look at the peak width as it is related to the resolution of separation, as you'll soon see. So resolution in chromatography is given by capital R sub S, can be defined as the difference in retention times between two peaks divided by the average width of the peaks. The shape of an ideal chromatographic peak is a Gaussian distribution. And as you know from studying Gaussian distributions in other courses, the distance from the inflection point on the peak to the center of the peak is the standard deviation given by sigma. In practical terms, this inflection point is hard to define on a peak from real data. And instead, in chromatography, we typically measure the width at the half height of the peak, because this is easy to measure, and use the relationship that the width at half height is about 2.35 standard deviations. And from this, we can indirectly measure sigma. Moreover, the actual width of the peak is defined as 4 standard deviations in chromatography. So using these relationships for defining sigma and the width of the peak, we can also define resolution as 0.589 times the difference in retention times divided by the width at half height, or we can define the difference in retention times divided by 4 times the standard deviation. Assuming the peaks are symmetrical, a resolution value greater than equal to 1.5 corresponds to what we call baseline resolution. That is to say, if we take this difference in retention times and multiply it by 0.589 and divide by the width at half height for each of these peaks, for this diagram, we get a resolution of 0.5. And as you can see, these two peaks are not resolved because they overlap, and when summed, give rise to a peak that looks like this. As the resolution parameter increases from 0.5 to 0.75 to 1 to 1.5, we see at 1.5 specifically that we have achieved what we call baseline resolution, meaning that the peak reaches baseline before the next peak begins. As long as we have resolution of 1.5 or greater, we can safely say that our two peaks are resolved. In summary, We have just learned that separation is based on the differential partitioning and migration between the stationary and mobile phases in chromatography, and that the area under a peak in a chromatogram is proportional to the amount of the analyte, and that chromatogram parameters of retention time and peak width, particularly the peak width at the half height, can be used to calculate resolution, symbolized by R sub s, and that well-resolved peaks have an R sub s greater than or equal to 1.5. In the next video, we'll examine the factors that determine resolution.